4-bit computer, the range of integers that you can take is between -8 and 7. And the first bit is the sign bit. Just one second. So the first bit is a sign bit, which is 0 if the integers that you want to store is positive, and 1 if the integers that you want to store is negative. And then if integer is positive, then the remaining 3 bits are just a binary representation of that. And if the integer is negative, then what you do, the first bit is 1, and the remaining 3 bits are obtained by the binary representation of that negative number by taking 2's complement. Another shorthand method for that was you add simply 16 to it, okay? And whatever number turns out to be, write its binary. For example, -3, if you want to express that, -3 plus 16 is +13, and +13 binary representation is 1101. So that is the binary representation of -3. When it comes to arithmetic, arithmetics works the same way. When you add two numbers, if the addition is within the range, then you will get a correct answer. If the answer is not within the range, it will show an error, just like the error you see on calculators. Okay? That simply means, error simply means that the permissible value is not within the range. So then we looked at this table, we constructed this table of 4 bits, that how numbers are stored. Okay? For our information purposes, this is enough. If you want to do that for 16 bits, then the range would be between -32,838, yeah, is that right? And to the +32,700, no, I'm wrong. If you're working on 16 bits, the range is -32,768 to +32,767. And if I'm going to write down all of them in table form, that will take me a few days. All right, so we don't want to do that. This is very simple. So you simply keep dividing by the number. Okay, so this is how these are stored. And if you want to add, okay, I'm only talking about addition. I'm not talking about subtraction, because subtraction can be written again in terms of addition. Instead of subtracting two numbers, I can write addition of one positive and the other negative number. Okay. Sometimes two numbers can't be added on a 4-bit computer. Of course, for example, if you add 4 plus 6, the answer would be 10, and that time 10 doesn't lie between -8 and 7. Right? So that would be an error. However, provided we look only at numbers that can be added, addition is carried out as usual for binary numbers, except that if there is a 1 in the 5th column, we ignore it. Okay? And if it's 0 in the 5th column, we don't. It doesn't matter anyway, because it's on the left side. Now, if we want to verify that the addition -3 plus 7 is carried out correctly on a 4-bit computer, what is -3? If you look at that, it is 1101 plus 7 is 110111. If I'm adding that, I'm going to get 0, 0, 1, 0, 1, and this is 1 in the 5th column. I'm going to ignore it. So my answer for that is 0100, which is equals to 4. Questions? So this is I'm still on the same lecture. You would have noticed by now that every lecture I start off with the revision of the previous lecture, what we did, just to recall where we were previously. Okay. Overflow problem that I just talked about. What happens if we try to add numbers whose sum lies outside the permitted range from -8 to 7? Okay. find 4 plus 7 using a 4-bit computer. If I'm adding 4 plus 7, that would be 0, 1, 0, 0 plus 1, 1, no, 0, 1, 1, 1. Yeah? So this is the addition of 2. I would have 1, 1, 0, 1. Okay. Which is 1, 0, 1, 1. It is equals to negative 5. Impossible, right? The sum of two positive numbers is negative. It's not possible. So that's where it will show an error, which is called an overflow error. Okay. Here, two positive numbers give you negative 5, which is wrong. So this illustrates an overflow problem. Overflow also occurs when two negative numbers are added and your sum is positive. So to deal properly with overflow, a 4-bit computer should generate an error message when it occurs, of course. Similarly, if you have a 16-bit computer, similar kind of things would happen, and it should generate an error if that happens. Okay. As the last item says, overflow can occur no matter how many bits are available for integers, and needs to be considered when designing a computer's inbuilt routines or writing programs. So now when you wonder why you're getting error message on your calculator or anywhere else, you know why. Okay. Make sense? Lovely. Now subtraction in a computer. I already have talked about this. Okay. Subtraction of integers using computer representation is straightforward because the subtraction a minus b is the same as the addition a plus minus b. So advantage of doing this, as you correctly pointed out in the previous lecture when I asked this question, is that in the circuitry we would only have to deal with one operation. The representation likely b is the 2's complement, whatever that is just a representation of that. Thus, subtraction is performed by adding the 2's complement of the number. Why is the 2's complement method used for subtraction in a computer? Because the method does not require a computer to have subtractors in its circuitry. We don't want another operation to be used in a circuit. Our keys are very precious. So we want to use them effectively. If a thing can be done by simple maneuvering of another operation, then we would do that. We wouldn't have to introduce a absolutely new key to it. Okay? So this actually gives you an extra speed if you have only operations take plenty of space. And you have to introduce them in circuits inside and all that. So you have to be careful. Already there are 2's complement there. So if 2's complement there, then we don't have to worry about subtraction anyway. Okay. So what happens when you're doing arithmetic with more than 4 bits? The method is the same, right? The methods we have described for integer representation. 4 bits also extends to other numbers. Verify that minus 43 plus 26 is evaluated correctly on an 8-bit computer. If I want to do that, how I would proceed? I would write down what's the binary representation of this number and what's the binary representation of that number. Can you help me with that? So you've just done these questions there. So can you help me finding these binaries? The number that I got from negative 43 is this. Is this correct? Okay. So we would add this to 26 plus minus 43 would be equals to 0, 0, 0, 1, 1, 0, 1, 0 plus 1, 1, 0, 1, 0, 1, 0, 1. And they're binaries. Yeah? So what is this number? Let me write it down carefully. 0, 0, 0, 1, 1, 0, 1, 0. So the other numbers are 1, 0, 1, 0, 1, 0, 1, 1. I'll add them up. Yeah. So that is going to be 1, 1, 1, 1, 0, 1, 1, 1. So this is equals to 1, 1, 1, 0, 1, 1, 1, 1. Now, what is this number?
Negative 23.
Yeah, it should be negative. No, hang on. Why?
Sorry, I screwed up.
So firstly, this one indicates it's a negative number. Yeah? So we have to find out what is this number. Yeah, well, from here I can do that, but can you verify that? Please.
Should we just call for that again?
Yes. How would you do that? Have you got the right answer? Who has completed this question? Take your time.
What are you up to on this?
Yeah.
Which question are you on this sheet?
I want you to verify what number you're getting here. It's a negative number.
Oh, okay. Yes, I can see. Let's work on the solution.
How would you do that?
Would you choose complement reverse, reversing the first bit, and then keeping the first one and inverting it?
Why?
Because the conversion to negative is the same, so if you do it backwards, it should be the same.
Fantastic. Yes. That's right. If we are writing a negative number in binary representation, how we do that? We start off, before I just quickly throw an answer, it is important that we understand the mechanism. So the mechanism is, when you're saying that you have a number, negative 17, okay, its binary representation is that your first digit would be 1.
Sure.
And after that, to represent its the rest of the digits, 1, 2, 3, 4, 5, 6, 7, 8. So to find rest of the digits, how we proceed, we divide 17, we find binary representation of 17. That would be 8, 1, 4, 0, 2, 0, and 1, 0. So it would be 1, so you would have 1, 0, 0, 0, 1. Okay. Yeah? Okay. Basically, this way. So, but then these two are extra spaces, there you have to put trailing zeros. So this is the binary representation. Still not achieved that yet, because we have to put 2's complement, and 2's complement is, I should not have put actually this there, I would have to flip it. One stays the same, trailing rightmost zeros, as well as rightmost one stays the same, and rest you flip them. So this goes, this is 1, that is 1, that is 1, this is 0, that is 1, that is 1. Okay. So basically what you did, these numbers, so this was 1, 0, 0, 0, 1, 0, 0 here, don't touch this 1, okay, the rightmost one stays the same, and flip the rest. So you have this one as it is, and then you're flipping the rest. That's your 17, negative 17, where this negative, you put 1 there. Now look at this representation here. Okay. So the representation for that number, this sum is equals to negative 17. Again, if you did not understand that, let me explain that again. This is important. How do you do that? Okay, well, let me start off where we were. So you have number negative 43 plus 26. You want to do that. And what you did, you simply started off by adding 26 and negative 43. So you have to find their binary representation. What is 26 binary representation? You divide on 2. You have 13, 0, 6, 1, 3, 0, 1, 1. So you would have 1, 1, 0, 1, 0. Yeah. So this is for 26, right? But these are not 8 bits, these are 3 bits, these are 5 bits, so I need 3 more zeros, where the first one indicates that it's a positive number, and the remaining 2 are extra zeros to make it 8 bits. So this is your 26. Now negative 43, if I want to do that, then I will think of the first bit is 1, because it's a negative number. Now I have to find the remaining 7 bits. 7 bits you would find out by dividing 43 on 2. You have 21, 1, 10, 1, 5, 0, 2, 1, and 1, 0. So these numbers are 43 is equals to 1, 0, 1, 0, 1, 1. Okay? But what you need 7 bits here, not 6, so you put an extra 0 there. But you're not done there yet, because now you're going to apply 2's complement. And what is 2's complement? 2's complement is, don't touch this 1 on the rightmost, or don't touch rightmost zeros and the first one that you get. So this one stays the same, and you reverse the rest. So you would have 0, 1, 0, 1, 0, 1, and you put this number here. That would become 1, 0. 1, 0, 1, 0, 1. Yeah. So these are your binary representation for 43. Now, what is next? Next is that you add them up, right? So I'm going to add them up. Yeah, it's just taking time. Okay, since we've done that, so I can erase it. Now, I put the numbers up here and add them. Oh, this is too thick. Oh, that's what I thought. Okay, so you have 0, 0, 0, 0, 1, 1, 0, 1, 0. This is your 26. And the other one is 1, 1, 0, 1, 0, 1, 0, 1, and you add them up. Okay. When you add them up, what your answer is 1, 1, 1, 1, 0, 1, 1, 1. All 8 bits. So Negative 43 plus 26 is equals to 1110111 to the base 2. Now I want to identify what this number is. This is a stored number, remember. It's not the usual binary conversion. The number is stored in a computer. Once I say it is stored, then you have to find out, you only look at this binary. You're looking at the binary representation, and it's a stored binary representation. If it's a stored number, then first thing we have to see whether it's a positive number or a negative number. Since the first digit is 1, that's a negative number. Next, you worry about the remaining 7 bits. So the remaining 7 bits now, you go that reverse process of 2's complement. So the rightmost one stays the same, okay, and then you reconvert them. So you would have one, the rightmost one stays the same, and the other numbers you flip them 0, 0, 0, 1, 0, 0. And what is this number? This number is 17. You can see 2 to power 4 plus 2 to power 0. So it is 17. There you go. First one is negative, and then that number is that. So since this is in range, in 8 bits computer, what is the range on 8 bit? 8 bit range is negative 2 to power 7 to 2 to power 7 minus 1. So basically it is negative 128, 227. On 8-bit computer, the range of integers is between negative 128 to 127. Yep. Any questions? Yes.
Is there a way to get past the range without overflow, without moving to a different base?
Without moving to a different base, what you mean? That has different base has nothing to do with overflow.
Not different base. I mean,
No, you have to increase to different bits.
Yeah.
So instead of using 8-bit, you want to use then 16 bits. Or 16 bits, if there is overflow problem in 16 bits, you want to go on 32 bits. 64, 128, and there are always restrictions on computers. Up to certain limit, they can calculate things. After that, they can't. Whatsoever, even you take supercomputers, there is a limit. They can do up to 9 billion or 9 quintillion or whatever number, but it's a finite number. After that, they can't calculate. They show us an error. The entire research, entire mechanism, everything that we are doing is to improve efficiency of computers, improve their accuracy. And overflow problem always occurs. Yeah. Okay, so we verified this. The methods I have systematically described. First, find the 8-bit representation of both the integers, take the 2 complement of a negative number, add them up in their binary, and then identify whether the binary representation is of a positive number or a negative number. Once you identify it's a negative number, then you have to apply 2's complement in inverse, right, conversely, and then that's your number. If the leading bit is 0, then you don't have to do anything, just convert that binary into that number, decimal, and that would be your answer. Okay. Now, computer representation of a real number. Remember, so far we only talk about integers. We have not talked about so far about real numbers yet. This will be then this is handled quite differently. Okay, this is not exactly the same way as integers. Okay, computer representation of real number is based on exponential notation. If the number is real, we would write it down slightly differently. And normally for real numbers we need slightly expanded bits. We don't work with 4 bits then anymore. We normally work with 16 bits or 32 bits. Okay? In 32 bits is slightly easier and more accurate than working on 4-bit. 4-bit is not that handy anymore. Okay, what is exponential notation? Anyone?
When dealing with really large value sets, so I'm trying to think of a real world example, but say if we're dealing with really high temperatures or something, then you notate that as an exponential. That's sort of where you're going with that.
Close to that.
Close to that.
Sort of is very big number, then or very, very small number, you write them in exponential form. Anyone else? Can you give me precise definition, anyone?
So like x times 10 to the power of 6 or something.
Yeah, that's exponential form. Okay. Yeah, you're right. Exponential form is when you write a number in powers of tens. NASA states that Earth mass is 5.97219 times 10 to power 24 kilogram. What that mean? That means the number is 5972191 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 and then these 5, it makes 24. It is this number. Now you can see advantage of writing in this form is for convenience, right? Yeah. So basically, instead of writing all of these zeros, you only write first few bits here times 10 to power 24. Now, this number may well be 5.9 times 10 to power 100. I would not want to list all the 100 zeros there, right? Nobody wants to do that. So exponential form is really handy, easy to deal with. However, it comes at a cost. What's the cost? Yeah.
$24.
Yeah. I can buy it for 20.
Accuracy.
What's that?
Accuracy.
Absolutely right. Accuracy. What is inaccurate thing here? If I'm expressing my actual value in this form, what is inaccurate about it? Writing an exponential form is sort of inaccurate in certain sense.
Get a rounded number.
What?
Get a rounded number.
Yes, sort of. Yes. So you can see there are 19 zeros here. These are not necessarily 19 zeros. These are some positive numbers there, like 1, 3, 5, something like that. So, well, writing in this form is sort of substantially inaccurate. Convenient, but inaccurate. This is just like if you have a number 5,944, right? And you simply write it 5 times 10 to power 3. Yeah? If you write it 5 times 10 to power 3, this number is 5,000. But this number is 5,944. So this number is slightly inaccurate, although convenient, but inaccurate. Yeah? So that convenience comes at a cost. So there is always possibilities of error. Mm-hmm. Okay, there are two reasons for not doing this. It is, you don't want firstly to write all of that, okay, whatever the big string of number that you got, you don't want to express that full string because of course it's inconvenient. Second, it's too big, really. Storing then becomes a problem. Why? Because when you convert that into binary, that big integer, how long you can divide it for? It takes really the processor speed. And also it is, as I said, sort of, if I write it down in this form, 0, 0, 0, 0, 0 full, it is wrong, right? If I put all the zeros there, not necessarily, right, that all 19 digits are zeros. Okay. Anyway, let's look at exponential notation in detail. 5 point this is said to be written in exponential notation. This notation is especially useful if numbers are very big. As I said, 5.9 times 10 to the power 100. Of course, then it is useful, right? We don't want to list all the digits there. Or numbers very, very small. What you mean by numbers very, very small?
The negative powers.
Absolutely. If the power is negative. Okay. Example, 5.9 times 10 to the power minus 10. This number is 0.0000 up to so on. There are 9 zeros and then 5 9. This is a very, very small number. Yeah. In this expression, this number is called significant or mantissa. You haven't done maths in 90s when we haven't had luxury of calculators. At that time, we had manual tables to calculate logs. Do you know logarithm? Right. So we've been getting these significance in a printed form to do them instead of using calculators. Well, here, okay, let me then. This number is called significant. 10 is the base and 24 is the exponent. Okay, just the notation purpose. If the significant m is in the range, so this significant, we always want it to be in the range between 0.1 and 1. Significant will always be that we would store in computer will be in this range. And this is called normalized. So whenever you get, I would normalize this as, I want to normalize it, so this would become 0.597219 multiplied by 10 to the power 25. I would shift the digit, the dot here, to bring that within the range of 0.1 and 1. So this is called normalized range. This is not normalized, however, this number is normalized. Okay. So we always want that significant to be between 0.1 and 1. Exponential notation is the basis for how real numbers are represented in a computer. Although powers of 2, not 10, are used, and exponent is stored in a modified form. So we will not be using to power 10, we'll be using to power 2 because that will be the binary representation. Okay, that's what we are dealing with. Now let's look at the normalized binary exponential form. Before finding the computer representation of a real number, it must firstly be converted to binary, then expressed in normalized binary exponential form. So first step, convert a number into binary, whatever number you're given. Then express that number into normalized binary exponential form. That is significant value, that is m times 2 to the power whatever the exponent that you're getting. Let's say e, exponent, or some number a, doesn't matter, right? So A number is in normalized binary exponential form if it is expressed as in this way, where m is between, the significand is between 0.1 and 1. E is the decimal integer, whatever the power is, okay, and 2 is the base, of course. Some computers use the significand between 1 and 10. It does not matter much, but we will stick with the notation between 0.1 and 1 here. Okay. Express this number in normalized binary form. So let's look at this number. What I want to do, I want to write this number in this notation. Okay, so what I want to do, I want to shift this decimal here. I would have 0.101110101. How many points I shifted? 1, 2, 3, 4, 5, 6 times 2 to power 6. Okay, make sense? So this is the normalized binary exponential form. So in the next lecture, we will learn how this is stored in computer. Not very difficult, it's simple method though. Yeah. So we have to identify whether it's a positive number or negative number, and then we have to put significant there, and then we have to put how many, what is the exponent there. It's not that, it's very easy, okay, but we need more than 4 bits now. Okay, so we express this in this normalized binary exponential form. Here is an exercise for you. Can you write this in normalized binary exponential form? It's not in the normalized binary exponential form. That's the first step to notice, because the range, it has to be between 0.1 and 1. This is 0.000001, which is less than 0.1. So it is not normalized. We want to convert that into normalized form. So you want this decimal to move here. Yes.
So is that 1101 times 2 to the negative 4?
Yep. So 1, 2, 3, 4. So you move this decimal here. So your answer is 0.1101 times 2 to power negative 4. This is a very, very small number, as you can see, right? And from there, if I'm moving my decimal to the right, I would have power in negative. If I'm moving my decimal to the left, my power will be positive. So this is how these exponents work, right? And I note that 0 cannot be written as normalized binary exponential form. Okay. 0 times 2 to power 0 or something. So we are taking convention that we will not write it as, it's totally throughout the 0 string, so there's nothing to store about. It's an integer. It's not a real number. So, yeah. Any questions? Anyone? Come on, we should have some. Go and watch imitation games if you have not done so. I would ask you a few questions about that at some stage in this subject. No, homework is to do the exercise. It does. Okay, let's say it does. I want you to understand why he said that, why the 5 bits there he ignored. So, if you understand that, you've done the work. What's that? I don't get it. Oh, you don't want to go home? Yeah, go then.
I have enough chance to make myself drunk.
Man, I looked at my face on stuff the last time. I was like,
What happened last night?
the malt launch party. The malt launch party.
I did say something on mine.
Hopefully it's not bad.
BSA stuff.
Yeah.
All right, fellas.
See you next week.
See you, man.
Alright.
Yeah.
Okay, right.
Yeah, and then all of a sudden everyone starts.
Yeah.
See you guys.
I'm Christina.
We have a whiteboard, that's good.
We have everything. Excellent.
We do over there.
Yes.
How handy is that?
It's a little bit funny set up.
Yeah, I'll mainly use here because it's in front of you, which is always better. Sort of big binary numbers because they're sort of distressing enough.
You brought that other textbook in with this place. I don't know if I looked at the reading list. It's not on there. I don't know, they sent an email saying that you had to have it. I know, but it's not actually on like the student learning guide.
For any of these? I think they said it's for week 5 groups.
Yeah, but the student learning guide should have textbooks. Like it has these two. And I was like, oh, okay, well that's lovely.
Yeah,
And she sent an email
saying we need it.
and I still let them move it.
Yeah, and then but like I think
Wow.
it's just been published like
So much
this month,
technology.
last month. Because it said July 2019. So I don't think you can even get this in hand. So they said they had that link to get it on the actual Thomas Reed website.
They are really good. I just got mine a little bit from the week. It's amazing.
I ordered mine. Whoa.
And I ordered it like Thursday.
I ordered mine Wednesday, and it was like $127 or something. Then the money is back in my bank account, but it doesn't say it's been taken out or gone back in. But I got the confirmation email. And I was like, that wasn't there yesterday. So I forget what that is. But it says it's been paid for.
That's odd.
Yeah. I'm like, okay, yeah. Yeah.
Do you know what's happening with the textbooks?
I know there's been a delay, and I've heard it might be quicker to go straight to the publisher.
Yeah,
But
the email that they sent out, the textbook I couldn't find it on like the student learning guide for scribed reading at all. So I'm just confused as to why we need it, but it's not in the guide at all.
okay,
It has to do with the actual course. It's
that I'll have to ask Barley.
Is that the ACL one?
The consumer law.
Yeah,
Yeah.
fairness. I've certainly got it, but then I got it given to me. It looks like this.
well, that's a pretty textbook cover for most.
Oh yes, I like it too.
This is not super fat either.
So it's certainly something we'll be using
It's a full
in shoots.
Yeah. Is it new this year? Because I swear it said 2019.
Yeah, there's 2019 on this book.
Yeah,
There
so
you
I
go.
don't think you can get it in here either. That'll work.
That's fast, isn't it? Yeah, I'm fully sympathetic because how much was it?
They gave us a discount to get it through the
Yeah,
publisher.
you get 15%
It was
off the
still
students.
like $130,
Yeah, that's
which is pretty expensive considering you've already bought those two.
I was going to say, it was secondhand when it was costing $300.
I thought this was $60 each secondhand, but brand new they're like 100 and what? 120?
170.
Yeah.
I know we won't be using this for a number of weeks anyway.
Yeah.
So you might want to just sit tight and see.
Narrative says they okay, it said amendment to student learning. That kind of answers my question.
What I want is OneDrive. So it's been a late edition, has it?